Hey, here we are again. For today's lesson, we're going to be talking about induction and energy transfer. All right, this is chapter 30.2 and 3, sections 2 and 3. So, the first thing I want to do is I want to remind you about what we discussed last time. That was Faraday's law. We said that for any loop in a magnetic field, if there was a changing magnetic flux through that loop, then an EMF would be induced in the wire, right? Of course, an induced EMF also produces a current, and that induced current would have its own induced magnetic field associated with it. And that's where Lenz's law came in and said that the directions of all those things were such that the induced magnetic field would be, or the induced current would be in such a direction that the induced magnetic field would oppose the change in flux. Okay, so that was Faraday's law. Today, what I want to do is talk about some more about that. What I've got here is a loop of wire. Okay, this is my loop of wire. It is in the presence of a magnetic field. That magnetic field is into the board. There are dimensions of the wire. I've got a length vector or a length dimension here, and I've got a sort of a width dimension here. This is the portion of the wire that is in the magnetic field. What I want to do is imagine that we grab a hold of this wire and pull it this way, right? It's moving that way. We grab the wire, right? We go, oh, there we are, right? It's a little hand, and we grab the wire and we move it. Well, sorry, if it was me, sorry, it'd have to be like this. There we go. All right, boom. We grab the wire and pull it that way. Okay, so we get the wire moving with some constant velocity in that direction. Okay, now what that means is that the flux through the area of the loop is going to be changing, right? This dimension is going to be changing with time. Okay, so what that means is an induced EMF will occur. I want to find that induced EMF. Okay, well, we know that the induced EMF by Faraday's law is given by that expression. Obviously, we only have one loop. And in this particular case, for now, I'm only concerned with the magnitude of the EMF, so I'm not going to worry about the negative sign. And we get the rate of change of flux. Now, if you guys recall, flux was that area integral of B dot dA. We can reduce it down to the full magnetic field times the area times the cosine of the angle in between those two. Now, in this case, I'm going to say the area vector is into the board, and the magnetic field's also into the board, so this cosine reduces to 1. And the magnetic field is constant in this case. What's the thing that's changing? Well, the thing that's changing is actually the area of the loop that's in the magnetic field. Okay, so how do we define that area? The area is going to be the length dimension times the width dimension. L times X. All right, now in this case, even the length is not changing, right? The thing that's changing is the X dimension. Since our loop is moving out of the field, it's the X dimension that's changing. So we're going to write this as the EMF is equal to B, pull the L out, it's constant, times the dx dt. Okay, now if you all recall, the rate of change of position, dx dt, what is that? Well, that's our velocity, right? Velocity by definition is the rate of change of position. So in this case, we end up with an EMF, the magnitude of the EMF, as the magnitude of the field times the length variable times our velocity, okay? Okay, so we can do some more work with that. The next thing I want to talk about is what is the current itself, right? There's our induced EMF. We'll have an induced current associated with that EMF. We know by Ohm's law that the EMF is equal to IR. So saying that this wire has some resistance associated with it, then we could call the induced current as just EMF over R by Ohm's law. So subbing in our expression for EMF, I put that the induced current is going to be equal to the magnitude of the magnetic field times the length times the velocity over the resistance. Okay, we know we have an induced EMF. Let's look at the direction of that EMF. So remember, by Lenz's law, right, it's going to oppose the change in magnetic flux. So as this loop moves out of the magnetic field, we have a decreasing area which is in the magnetic field. That means a decreasing magnetic flux. So if our original magnetic field is into the board, we have a decreasing flux. So our EMF wants to oppose that decrease. Then we would get an induced magnetic field also into the board, right? It's going to want to keep that EMF, or it's going to keep that magnetic field large. So we'll have an induced magnetic field into the board. All right, so the direction of our induced current, which is associated with that magnetic field, via our right-hand rule, thumb goes in the direction of the magnetic field, our fingers curl in the direction of current. So our induced current would be clockwise around this wire. Okay, there's our induced current, clockwise around the wire. Now, while this is going on, what you'll notice here is that along this length of wire, and there's a current in the presence of a magnetic field. You know from, I think it was from chapter 28 or 29, that a current in a magnetic field will experience a force, right? We defined that as IL cross B, right? Where the length vector was the same direction as the current, conventional current, and the magnetic field vector there, right? Now for cross products, remember, cross product says that we've got the magnitude of all the vectors times the sine of the angle in between those. So in this case, we would have the magnetic field into the board, the current is up, so the angle between those two vectors is 90 degrees, the sine of 90 is 1, so that goes away. I can sub in my expression for the current here, right? My current was BLV over the resistance. So I've got two B's and two L's. I've got a B squared, an L squared, a velocity over our resistance. There is the force that will be felt by this wire. Now, what's the direction of that force? Remember, IL cross B, we use the old physics gang sign, right? Pow, watt op ohms, right? So first finger goes in the direction of the current, middle finger goes in the direction of the magnetic field into the board, our thumb points in the direction of the force. So the force on this wire would be in that direction. It turns out it's exactly opposing the force that we would have to be applying in order to move the wire out. The next thing I want to talk about is the power, right? Power being the rate of work. So if you recall, power is the force times the velocity, right? If that's a little tricky for you, remember work. Power is work over time, right? Where work was force times distance, let's say x. Put that over time, we get x over t. If there's a rate of change of that, then it gets velocity. That's how we get to this function. This was from last semester, so I'm not expecting you to know this offhand, but that is the case. All right. So if power is the force times the velocity, well, I have my reference for force over here. I'm going to write in, I've got b squared times L squared times velocity squared times another velocity, so I get all of those top variables squared over the resistance. Now I want you to hold that in your minds for a second. That's the power, that's the rate of work that we are doing, right? To pull this to the right, right? Because it turns out, remember, that force is exactly opposing the force that we are applying. However, we can also define power in terms of the rate of change of energy in the wire based on the current, right? This is sort of like the resistance. Resistance is the energy dissipation rate, right? So if you recall from circuits, we said that the power in a resistor was I squared R. So if I put my I value, I square everything in here, right? I get the magnetic field squared, the length squared, the velocity squared over the resistance squared, and then I multiply by a resistance, right? This R and one of those R's cancel, and we end up with the exact same value of power based on those two definitions. Okay, what this means is that the amount of work that you are doing in order to move this loop out of the magnetic field is the same amount of work that the resistance in the wire will transfer away from mechanical work into heat. Okay, it's the rate of change of energy. All right, so a way to rewrite Faraday's law. Remember back in like chapter 25 or 26 maybe, when we first introduced electric potential, right? We first introduced electric potential. We wrote that the EMF is equal to that the line integral E dot ds, right? That's how we wrote that. I think that we might have had a negative sign in here, but recall that depending on the direction that we took, remember this EMF is just a rate of, or is a change in potential, right? V final minus V initial. So depending on which direction you go, we can get rid of the negative sign there, right? So essentially, we have this definition of electric potential based on the electric field, and we have this definition of electric potential based on a changing magnetic flux. And both of these, right, we can equate since they're electric potential. So we can rewrite Faraday's law in terms of an electric field. We can say that the integral of a closed loop, this is a closed loop, right? It's a loop sort of around the loop. The integral E dot ds, we take a path around a closed loop. We can set that equal to the negative of the rate of change of magnetic flux. This is just a rewrite of Faraday's law, and it allows us to take this rate of change of flux and equate it to an electric field. An electric field created a magnetic field, right? If you had moving charge, a changing electric field, essentially. You have a moving charge, you have current. Current creates its own magnetic field. Well, the opposite is also true, that a changing magnetic field creates an electric field. That was actually pretty novel at the time that it was discovered. All right, that's all we have. We'll do one sample problem. I hope you have a great day. Oh, by the way, by request, smash that like button. Be sure to subscribe. All right, take care.